Hi, I'm J.Jamison, and this is my DSP final project, leveraging software-defined radio for wireless channel characterization. So wireless channel characterization is important both for determining the requirements of a wireless system as well as the system's resulting reliability, and it's especially useful in environments with a lot of multipath. The goal of channel characterization is to represent your wireless channel as a digital filter both in the time domain and the frequency domain. So software-defined radio has recently been proposed as an alternative to traditional radios, where you implement things entirely in software instead of hardware. So basically the only thing that happens in hardware in a software-defined radio is the down conversion and then sampling of your signal, and then that sampled signal is sent to a computer where DSP is used to do any of the modulation or demodulation of your signal. So a low-cost software-defined radio-based channel sounder will allow for far more accessible channel sounding, both in terms of price point and portability. So recently, this has been a topic of research. So in this first citation, this group had a high-end measurement system that used a pretty expensive software-defined radio, namely the Edis Research X310. The system wasn't distributed, so basically the transmitter and the receiver were running the same program from the same system, so they had to be connected to the same point. And in the second citation, there was a distributed system. It was lower cost radio, but it was only demonstrated in a hardwired simulation environment over 40 megahertz of bandwidth. So the goal of my project as a whole, which extends beyond the scope of just this class project, is developing a low-cost software-defined radio-based channel sounder that can characterize multiple links simultaneously over at least 80 megahertz that's fully distributed. So far, I've come up with a scalar measurement system with an average error of about half a dB between my system and VNA measurements. So for this specific class project, I want to explore adding phase measurements to my system. So how I'm thinking about doing this is based on the idea that phase shifts in your signal are going to show up as rotations in your constellation plot. So if I transmit known symbols called pilot symbols from the transmitter to receiver, I can look at my constellation diagram at my receiver and calculate the phase shift of my signal. So some of the tools I'm going to use in this are pulse shaping, QPSK modulation, and K-means clustering. Pulse shaping is similar to windowing. Use it to round the edges of digital pulses in the time domain so that less high frequency content is needed to represent them. QPSK modulation is a form of digital modulation. We use a complex number to represent each transmitted symbol. And K-means clustering is a clustering algorithm used to partition in observations into P partitions. I basically use it to group my complex received data into 4 clusters to estimate the position of my constellation points. And Python library SciPy has a K-means function that I used for this. And I use GNU Radio Companion and HackRF Radio for this project. GNU Radio is an open source software that allows easy interface with software-defined radios and includes lots of pre-made DSP functionality as function blocks, and also allows for the custom function creation in either Python or C++, and I use Python for all my work. All the data in this is represented as NumPy 64-bit complex numbers. Some of the data is simulated in GNU Radio and others captured over the air and sampled to the HackRF, and I'll specify when each is happening. So first I have a little demo of my simulated program. So all this data is being simulated directly in GNU Radio. So basically I'm transmitting this constellation diagram through a wireless channel, simulated wireless channel in GNU Radio, where I add some noise to my signal, and I also add a variable phase shift. So I can see this is my received constellation diagram. I'm transmitting this symbol right here at 1/4 of the amount of times. The idea is that at my receiver, I'm going to detect which constellation point has fewer symbols around it, and to know that that one started out at angle 0. So whatever angle is at my receiver is the phase shift. So basically the phase I enter here is the phase that is going to go into my simulated channel, and the numbers that are being spit out down here are the calculations in my receiving program that are estimating the phase shift. So right now it's at 0 degrees. Let's say I wanted 45 degrees of phase shift. My constellation diagram will rotate about 45 degrees. You can see that this point, the one that has the fewer number of symbols around it, is now at 45 degrees, and my program is estimating a phase shift of about 45 degrees. This works pretty well through a wide range, all the way from minus 180 degrees all the way at full 360 degrees of rotation to plus 180. And if you look at the transmitted signal, you can see some of the rounded edges from the pulse shaping. These pulses would be much more rectangular if I didn't have the pulse shaping in there, and a relatively narrow transmit band, which would also be more wide band if I didn't have the pulse shaping. So I also have a video of a demo I did in the lab. So this data is actually collected over the air between my receiving and transmitting antenna. So that's the constellation diagram of my receiver, and this is the phase shift. What it's measuring is the phase of the received signal from transmitter to receiver. Receiver's on the right, transmitter's on the left. You can see that as I start to move my transmitting antenna further back, that's changing the phase shift, or the phase of the received signal. You see the constellation diagram start to rotate, as well as my calculated phase shift number change. And if you look at the spectrum of this signal is relatively narrow. It's only about 100 kilohertz or so wide, maybe a couple hundred kilohertz. So a pretty narrow signal. The idea being that I want to transmit multiple copies of this across the band. So the idea is I'm thinking that I can extend this over. So basically, show that this works well as single frequency, but to really get your frequency response, you need to do this measurement at multiple points in a band. So I'd like to extend this to multiple frequencies. The way I'm thinking about doing that is if you just transmit multiple copies at a single time, basically these triangles would represent other copies of that signal. And on my receiver, I could have a receiver with a variable center frequency where I could kind of move that receiver around until I aligned with each one of these, calculating the phase shift at each point. So as I started looking into doing this, I was thinking about maybe using an OFDM signal at my transmitter so I could get as many of these signals as close together without interfering with one another. And as I started researching, it turns out that OFDM channel estimation using pilot symbols is already a very well documented idea. So basically, using some ideas from estimation theory, you can compute the maximally likely estimate of the channel's impulse response with a simple equation at the bottom, where XP is your transmitted pilot symbol matrix. It's a diagonal matrix of your pilot symbols, and Y is your received signals. Or symbols, not signals, sorry. So I created a simulation of this in GNU Octave, which is basically just an open source MATLAB, to test this out. So this H right here is my channel impulse response, or the response to my actual channel. It's relatively random numbers. This isn't based off anything. I just tried to make sure I had some complex numbers in there so I would get some phase shift. I have basically like OFDM transmission here. I loaded on the subcarriers, add my cyclic prefix. I have add some noise. I have it actually go through the channel, unload it from the subcarriers, and here I calculate my channel estimate. And so from that channel estimate, you can then take the FFT to get your your frequency domain information. So you see, if I look at the results from this, you can see that the black is the actual impulse response on the left, and the actual frequency domain information on the right, and the dotted red lines are my estimated values based on this OFDM pilot symbol estimation. You see that it's pretty accurate both in time and frequency. You can see down here these red points that are a little bit higher than 0 are due to noise. So I added noise in my symbols or into my system. So even with noise, it's relatively resilient, and I get pretty good measurements. I don't have any mean squared error calculations, but visually it looks pretty decent. So I was able to successfully measure over-the-air phase shifts from transmitter to receiver to a single frequency. And I also successfully simulated measurement of a band of frequencies using OFDM channel estimation. So in the future, I want to try to implement this OFDM channel estimator in GNU Radio. And I also want to look at using a simulation, or I also want to look at calculating this based on the minimum mean squared error as opposed to the least squares estimate. So the program I ran there was using the least squares estimate. I've heard that the minimum mean squared error estimate is more accurate, but also harder to compute. So I want to read about that and see if that's probable. And I also want to integrate this with my scalar measurement system. So to wrap up my presentation, I've showed two different methods for measuring the phase information. One is directly measuring the phase measurements by tracking the constellation diagram. The other one is through OFDM channel estimation. Most prior work in this uses OFDM channel estimation, so I think what an interesting contribution to literature would be to get both of these methods working and compare them. So I think that's my next goal. So in conclusion, this project, I showed that it was definitely possible to capture the phase information over a wireless link with software-defined radio. The next step is going to be to implement these methods into a functional system, and like I said on the last slide, my end goal is to get systems working that use both of these methods individually so I can compare them. And that's my whole presentation. Thank you.